like a solid to a liquid to a vapor and that kind of thing. The next thing I'm going to show you is called a heating curve. And this heating curve is really useful for us to actually calculate the amount of energy it takes to go from one state to another. All right. So on this one, I'm going to add some stuff as well. So let me start adding some fun things. First of all, this is going to be for water as well. Let's see if I can make a couple text boxes. Water. All right, so this is for water. Doesn't have to be. You can do it for anything. All right, next up, I'm going to make, see this says temperature, Celsius. I'm just going to make it up a temperature. So I'm going to make this negative 50 degrees Celsius. All right, so that's where I'm going to start, negative 50 degrees Celsius. And I'm going to go up to 125 over here. All right, so this is across from there pretty much. Oop, I'm going to move it up a little so just so we can read it. 125 degrees Celsius. All right. So if I wanted to start at negative 50 degrees Celsius and then I want to add heat, I want to eventually get to 125 degrees Celsius, I can't just go directly from negative 50 all the way to 125. And the heating curve is going to show you what happens. And the weirdest thing about it is it doesn't even look like a curve, right? Because this is the worst curve ever, right? Because it doesn't really curve. It just kind of has lines. But all right, that's neither here nor there. So let's kind of go through this. So if you start off with something that's with water, because we said this was water, right? So if you start off with water that's negative 50 degrees Celsius, what state of matter is it in? And you can just imagine it. Yeah, negative 50, it's going to be a solid, all right? So we have a solid, which is our ice, right? So starting at A, going up to B, it's all going to be solid. What's happening as we go from A to B? We're increasing the heat, and it's actually going to be heating it up. So this ice cube that's negative 50 degrees is then going to go to negative 49, then 48. And I'm not going to do all the numbers, but then it's going to go to negative 30, negative 20, negative 10, negative 5. So at negative 5, it's a warm ice cube. Now that sounds crazy, right? What ice cube is warm? Well, compare negative 50 to negative 5. That negative 5 is much warmer, right? If we were talking about like liquid water, if we said 5 degrees Celsius versus 95 degrees Celsius, one of those is going to be ice cold almost. The other one's going to be almost boiling, so it's going to burn us if we touch it. So with ice cubes, they still have temperature changes. So we're going to get all the way up to negative 1, and then we're going to get to 0. So right here, this is going to be 0 degrees Celsius. All right, so we have 0 degrees Celsius right in here. Let's change some numbers around. 0 degrees Celsius. And once it's at 0, it doesn't just magically become a liquid. It actually has both solid and liquid in there. All right, so what's going to happen is once it gets to point B, it's going to have enough heat energy where instead of the temperature keeps going up, the temperature stays the same, but it's melting. All right, so we have this melting point. So B is our melting point. All right, there's both solid and liquid in here. We call this a change of state because we're going from solid to liquid. Whoops, let's move that up a little. Oh, that's not what I wanted. There we go. All right, so we have it going from solid to liquid. And as you go from B to C, what's happening is it's mostly ice here. Then there's a little bit of water, a little bit more, a little bit less ice. And then about here, maybe it's half ice, half water. Now there's more water, less ice. Once you get to C, then there's no ice. No ice right there. And then once there's no ice, as you keep giving it energy, the temperature now can go up because it's all liquid. So if you have a mixture between a solid and a liquid, the temperature is going to stay the same until it's all one state, meaning all liquid, all right? Because it's using all that extra energy to actually change the state, because that takes energy to go from solid to liquid. All right, so now we have liquid, temperature's going up, everything's great, nothing interesting here. We go from 0 up to 100, right? Because 100 is the boiling point for water. So let's add that in here. All right, so now we have 100 degrees Celsius. All right, we're at 100. This is D. This is now the boiling point. Yep, sorry, here we go. Boiling point is D. We have now both liquid and gas, just like before. We're changing state. All right, we're changing state. And we would call this boiling between D and E. Oh, I missed one. Between B and C, we call this melting. All right, so up here at D, we mainly have liquid, right? And then it starts to boil. So then we have a lot of liquid, a little bit of gas. We get to the middle, half liquid, half gas. Now we have more gas, less liquid. Now we have all gas, all right? All gas. And then once it's all gas, we can start heating it up again. So this would be like you boil the liquid, and then you were able to capture the gas and then start heating that gas up also. Now, if you keep on heating up that gas, it's going to increase its temperature from 100 to what we were talking about, 125, which was what the max temperature was that we were going to in this experiment. Now, it doesn't matter what the final temperature is. It could be anything. I mean, it could be 130, 150. You know, this could be, instead of starting at -50, it could start at -5, all right? And you're still going to have to go through all these steps, all right? Where, you know, you start out as a solid, then you change into a liquid, and then you change into a gas, and then you heat it up, all right? So if you always go from, you know, something that's negative, you know, below 0 for water, and then above 100, you're going to have to go through all of these steps. Some of them don't have all these steps, though, all right? So, you know, and for example, if we started at like 70 degrees, you would start here as a liquid, and then you would only have a couple steps to go through, all right? Now, each of these sections, each of these line segments requires a certain amount of energy. So what we can then do is we can actually figure out how much energy it takes to do this, to heat up that ice cube, and then how much energy it takes to melt, how much energy it takes to heat up this liquid, how much energy it takes to boil, how much energy it takes to heat up this gas. We can add that all up and figure out how much energy it takes to take your ice cube and turn it into gas. And so if you thought that just waiting for a pot to boil on the stove was boring, wait till we have to calculate how much energy it takes to make that ice cube melt and then boil, all right? So that's kind of the plan with these heating curves. It's all about figuring out how much energy it takes to do all of this, all right? And there's a lab where we would normally just take some ice, melt it, heat it up, and boil it. So you're missing out on a very exciting lab where we would be, you know, doing that process to figure out how much energy it takes. And you could do the opposite too. You could start at the top as a gas, and then you could go all the way down to an ice cube. Now, we're not going to do that today. This is where we're going to stop.